Another very important topic is what we call the variable length subnet masking. So in that particular topic, we need to divide the organization into different buildings, and the structure of the network is as shown. So we have building A, building B, C, and D, and we have WAN connections between each of these routers. So one way to divide that into subnets is by calculating the number of subnets, which in that case is 7. So what we need to do is to borrow 3 bits to represent 8 different subnets. So in that case, we can divide the network using 3 bits borrowed from the host portion, and then we can set these bits to zeros all the way to ones. And in that case, we will end up with 7 different subnets and only one subnet which is not used. So this will be available for future growth. The problem with that is that we have 3 networks here. If we notice, we have the WAN networks. Each of these networks only need 2 addresses for the interfaces between these 2 routers. So although we have used 3 bits, which means that we have 5 bits for hosts, and that will give us 30 different host addresses for each network. So for this building is fine, for this building is fine, for all these buildings is fine. But here the problem is that we have 3 different networks. Each of them needed only two host addresses, whereas we have assigned 30 different addresses. So there are number of unused addresses which correspond to these 3 subnets. We have 3 different subnets. Each of them needed only 2, whereas we assigned 30. So we lost 28 different host addresses that are not used on this network. And this is a significant waste of addresses if we are looking for efficient design. So we ended up here with 84 different unused addresses for this subnet. For that purpose, if we notice that the problem with the traditional subnetting is that we need to divide the entire organization into equally sized subnetworks. And this is the main problem, because some of these subnets may have different requirements, different hosts, and the extreme example of this, as we said, is the WAN connection, which needed only 2 addresses, whereas we had to assign 30 different addresses. So instead, the internet developers have designed what we call variable length subnet mask, where we can actually take one of these subnets and subdivide it into subnetworks and borrow another bit or 2 from the host portion of this subnet and use that to subnet this network even further. And in that case, the subnetting is done at 2 levels or 3 levels. And this way we can divide the network address ranges more efficiently and assign the different ranges to the particular subnetworks based on the need. So if we were to consider the previous example, so we can divide the network, which is /24, into 8 different subnets, assign the first 4 subnets, which have the last byte 0 or 32 or 64 or 96, assign this to the 4 buildings, take the other 4 and select one of these subnetworks and subdivide it using a variable length subnet mask. And in that case, we can select the network with subnet number 111. So in that case, we can subdivide this network and borrow another 3 bits and assign only 2 bits for host, because we only need 2 addresses for the WAN connections. And in that case, we can subdivide this network into another 8 different subnets. So this will be 111 and then 3 zeros, all the way to 111 and then 3 ones. Use 3 of these sub networks for the WAN connections, and in that case it will be /30, and the rest will be unused for future growth. So that's one way of subdividing the subnets at 2 levels, or sometimes 3 levels, using variable length subnet mask. So this here shows how to configure the routers for variable length subnet mask subnets. So So building A and building B and building C, we can configure each router and assign the different addresses interfaces as we can see here. So you will be able to go through this in details in the lab. If we were to design the IP addresses for the last example without subnets, so this shows the addresses assigned without subnets. So building A will be assigned 0, 32, 64, 96. So these are the 4 buildings. And then the WAN connection, the first WAN connection will have address 128, and the second one will have 160 and 132. The problem with that is that, as you can notice here, the range of IP addresses is from 129 all the way to 165, which is 30 different host addresses or addresses that we only need 2 of them, and the rest will be unused. And in that case, we ended up with one unused range, which is 2 to 4, which is 3 ones in the subnet number, and the rest will be 0. And in that case, only this range is not used. We have only 30 addresses here that are not used, and they are available for future growth. And instead of doing that, we'll take one of these networks, let's say this one, and then we'll make all these 3 subnetworks as unused, and we'll take the last one and subdivide it using /30, and then for each of these subnets, we'll end up with only 2 addresses used, and the rest will be only unused. So in that case, we ended up with 60 different addresses available here, plus 6 times 2, which is 12, which is like 72 different unused addresses, which can be available for future use. So this is a more efficient way of subdividing the network into subnets using variable length subnet. So let's see this activity here. So this shows the subnet, a network with an address 192.168.5.0/24, and we need to subdivide that into subnetworks such that, without using variable length subnet mask, such that the number of hosts is 50. So obviously here we need 6 bits for host, and the rest will be for the network. So we need to borrow only 2 bits for the subnet mask. So instead of /24, it will be /26. So the new subnet mask will be 225.225.225.192, and the network prefix will be /26. So the first range will be, of course, from 0 to 63, and then from 64 to 127, and then from 192. Actually, there is a typo here, because this should be from 129 all the way to 255. So this number here should be 129, not 192. There are several typos in that activity, and we need to pay attention to that. So if we were to use variable length subnet mask, so in this next example, we'll take the second full subrange, which ranges from 64 all the way to 92, and then we'll subdivide it into, we'll subdivide it into 2 subnetworks here. So this example here shows how to calculate the new subnet mask. And here there are several typos here that will make this activity actually not valid, but we will try to highlight these typos. So the network prefix, of course, instead of /26, it will be /27. So we'll borrow 1 extra bit for variable length subnet mask. So remember the previous network ranged from 64 all the way to 127, which means that this is actually 0, 1, and all zeros, and this is actually 0 and all ones here. So we'll subdivide this network into 2 subnetworks. The subnets will range from 64 all the way to 95. So this is the first one, and the next one should be from 96 all the way to 127. Okay, which is actually, there is a typo here. So of course the new subnet mask will have 3 ones in the last byte, so it will be 111, and then all zeros. So this actually is written here. So let's see. So this is the new subnet mask. There should be two different addresses for these subnets. The one should be 64, which means 0, 1, and all zeros. And the next, because we have borrowed one extra bit, so this should be 0, 1, 1, and then all zeros. This is actually 96, which obviously is incrementing 1 after 95 here. However, if you look here, there's no 96. So there is a typo here that this should be 64 and 96. So if we put this here, this will give us the subnetwork address for both networks, 64, and this should be 96. And of course, the last range should range from 96 all the way to 127. So it should be 96 all the way to 127. And here, there's a typo here as well. So if we put this here, then yeah, it's correct. However, there's, as we said, there's a clear typo. Here, this should be from 96 all the way to 127, and this should be 96. Okay? So pay attention to that.